Hello, I'm Seema and welcome to part 1 of the chapter Chemical Bonding and Molecular Structure. Do you know, as atom was discovered and the structure of atom was being studied on, we had the Bohr's atomic model, Rutherford was working. Simultaneously, scientists knew that atoms or elements, they are not usually found in nature as single atoms. It was found they are found in the form of molecules or they are found in some form of a combined state. Except for noble gases which live by themselves, all other elements, they combine with other atoms and they exist in that combined state. So when they combine with atoms, it is as if you can imagine this is a noble gas, an independent atom, it lives by itself. But atoms of other elements, they are found to be present either as molecules or as solids which due to some reason stay stuck together and behave as entities, as those molecules or as those group of atoms. And it is as if there's some glue that's holding these atoms together, and the properties of these entities which are called molecules are different from those of the individual atoms, and they exist by themselves in nature and they are known as entities themselves to us. So the question is, why do atoms seem to combine? What are the forces that hold them together? What is the nature of this glue? What is holding them together? What is the reason for noble gases not to combine while other atoms stay in the combined state? All this study was being done. Now, the first approach to understand this glue or to explain this was given by Cossell and Lewis. Cossell and Lewis in 1916, they were two scientists who gave the idea, or they imagined an atom to be like a walnut. And like the walnut has a shell and a kernel, the kernel is the nutty part that you eat, and the shell is the outermost shell that comes in contact with the world around it. The nut inside is protected. And it is the shell which has to bear everything, the change in weather or whatever whatever it is touching, the contact. So it is the shell that might undergo any change. The kernel inside is protected. In the same way, they imagined an atom to be like that, and they said that the valence shell, that is the outermost shell, when you imagine the Bohr's model of an atom, the outermost shell electrons or the valence electrons are the one that participate in this bonding or this glue, act as this glue, and they are gluing together atoms. While the kernel inside or the nutty part inside would be all the electrons in all the shells which do not belong to the outermost shell and the nucleus. So the nut is the nucleus and all the shells but the outermost shell, they form the kernel, and the outermost shell is the valence shell which participates in chemical reactions and leads to the formation of these molecules or leads to chemical combinations. Now they had a strange view, they did not imagine the atom to be like a walnut. They actually imagined it to be a cube, and they said that it is like, a cubic box, a box that's a cube, and everything inside is the kernel and the cube is the valence electrons. And these valence electrons, according to our knowledge, as I told you in the previous chapter, that 8 electrons can be present in the outermost shell of an atom. So these 8 electrons were imagined to be occupying the corners of the cube. If you imagine this room to be a cube, the 4 corners on the roof and the 4 corners on the floor, those would be the points where the electrons are present. And these electrons were known as the valence electrons. So, what did they do? They said, now according to that, Lewis said that if we study the periodic table and we try to take the elements like lithium, whatever elements were known at that time, lithium, beryllium, boron, we knew how many electrons they had in their outermost shell. Their electronic configurations could be written. So he gave a way of writing down the valence electrons. And these symbols were known as the Lewis symbols. How do you write the Lewis symbols? Now these are the second period elements. Lithium has one electron in its outermost shell. So he said you could make dots on coordination sites. If there are 8 electrons, we can imagine 4 sides around the symbol, right? So there are lithium, we first fill 1 electron on all the 4 coordination sides, and then we start pairing them as the electrons increase. I'll just show you. Lithium has only 1 electron in its outermost shell, so we make 1 electron to show lithium. That is the Lewis dot structure of lithium. What would be the Lewis structure for beryllium? Beryllium has 2 electrons in its outermost shell, so we can make 2 electrons. It would be okay to make it on top. So we would make lithium, I could have started on top just to make it a little symmetrical, but you make just 1 electron for lithium, 2 electrons for beryllium. Beryllium has 2 electrons, so we will not pair them. We will first fill up the 4 coordination sites. So beryllium would have 2 electrons. I can make 1 on top and 1 on the bottom. Boron has 3 electrons, so I'll make 1, 2 and 3. So the 3 coordination sites, on 3 coordination sites. Carbon has 4 electrons, so we make 1 on each coordination site. 1, 2, 3 and 4. Nitrogen has 5 electrons, so we first make 1 electron on each coordination site. 1, 2, 3, 4. And then we start pairing them. So nitrogen has 5 electrons, 5 valence electrons, which would be represented as this. So if we come to oxygen now, oxygen has 6 electrons, so it would be 1, 2, 3, 4, 5, and we need 1 more, so there will be 1 more pair. So either you do it this way, or you could have 2 pairs here and a single here, right? So oxygen, carbon, nitrogen, oxygen. Fluorine has 7 electrons, so 1, the 4 coordination sites, 2, 3, 4, 5, 6 and 7. So you have 7 electrons. And neon has 8 electrons, so all the 4 coordination sites, on all 4 sides you'll have paired electrons, right? So this is how the Lewis symbols were written. Now these electrons, these pairs, they are known as the lone pairs. Whenever you have a pair of electrons like this, they are known as the lone pairs of electrons, or they are just lone pairs. Lone because they are together, and you imagine, if you imagine it in 3 dimensions, you would be expected, Cossel and Lewis would expect you to imagine these as the 8 corners. The 4 coordination sites are actually 1, 2, 3, 4 corners of the room. So the 1 pair is here, 1 pair is here, 1 pair is here, and 1 pair is here, and the symbol of the element is in the center. So this is how the Lewis symbols were written for elements. Now, what did Cossel and Lewis say about the chemical bonding? How would the atoms be glued together? What was the reason for this? You are aware that Cossel and Lewis, they gave a rule which was known as the octet rule. And according to the octet rule, they said that any element can never have more than 8 electrons in its outermost shell. And all elements, if they have less than these 8 electrons, they have only one aim in life, and their aim is to acquire that octet. There are exceptions, but we'll talk of them later. The exceptions, and we have rather studied a little bit about them in the periodic classification of elements. So this octet rule says that all elements try to acquire 8 electrons in their outermost shell, and they can do so either by losing electrons or by gaining electrons, or they have the third option of sharing electrons. So atoms, they always try to acquire 8 electrons in their outermost shell, which can be done either by losing, gaining or sharing of electrons, which is known as the octet rule, which was also given by Cossel and Lewis. Now, according to this, what did they say? What did they look at sodium and say? That sodium, it has, what is the electronic configuration of sodium? It has the neon configuration, that is, sodium is the 11th element. So what would its configuration be? 1s2, 2s2, 2p6, 3s1. So 1s2, 2s2, 2p6 is neon configuration. So we write neon here. Neon 3s1. Now, in order to acquire 8 electrons in its outermost shell, sodium has a choice. It can either lose 1 electron or it should gain 7 electrons. I told you in the previous chapter that losing or gaining of 1 electron is easy, 2 is difficult, 3 is very, very difficult, and 4 is impossible. So if it has to gain 7 electrons, if gaining 4 electrons itself is impossible, because gaining or losing requires energy, and the more you need to gain or lose, the larger is the amount of energy required. Therefore, so when this sodium, it has a choice either to lose this 1 electron and get the configuration of neon, or to gain 7, which is easier. Obviously losing 1 is easier. So sodium loses 1 electron and acquires the octet of neon. It gets the configuration of neon. What happens when 1 electron is lost? It has the outermost shell in sodium is the 3rd shell. But when it loses that electron, the shell itself vanishes, because now the shell is only imaginary. It's only an energy level. So as soon as the electron is shot out of that energy level no longer exists. And the one before it is completely filled, which it has 8 electrons in the previous shell. Therefore, sodium loses an electron and acquires the octet of neon. Now, if you have a chlorine atom, chlorine has atomic number 17. Its electronic configuration is neon configuration, 3s2 and 3p5. Now, it has 5 plus 2, 7 electrons in its outermost shell. It either loses 7 electrons and acquires the neon configuration, or it gains 1 electron and acquires the configuration of argon. Obviously, losing 7 electrons would be much more difficult. Gaining 1 electron would be easy. So, what does chlorine do? It gains 1 electron, and now its configuration changes from neon 3s2 3p5 to 3s2 3p6, which is the configuration of argon. So, it now has 8 electrons in its outermost shell. So, this is what Cossell and Lewis told, that atoms, they try to acquire the octet either by losing electrons or by gaining electrons. And when they do so, now as soon as this loses an electron, the number of protons is the same. Therefore, this acquires a positive charge. When it loses a negatively charged electron, in neutral sodium, there were 11 electrons and 11 protons. But in sodium ion, there are 11 protons but 10 electrons. Therefore, this has 1 extra positive charge. So this becomes positively charged. While chlorine, it had 17 protons and 17 electrons. By gaining 1 electron, it acquires 1 negative charge, 1 extra negative charge. And therefore, chlorine becomes the chloride ion, which has a negative charge. And now, due to, we know electrical charges, when they are opposite, what do? They attract each other. And it is this force of electrostatic force of attraction which keeps the two together. So in the case of this sodium and chlorine, this kind of a bonding which is formed when a positively charged ion that is formed by the loss of an electron of 1 or more electrons, and a negatively charged ion which is formed by the gain of electrons, these species which are charged, they stay together due to electrostatic forces of attraction. Such a bond is known as an electrovalent bond. So this is one of the types of glues that hold sodium and chlorine together. The glue that holds ions together are called ionic bonds or electrovalent bonds. Right? Another example that we can take here is, you have calcium. Calcium is potassium, calcium. It's the 20th element. So what would the configuration be? Argon 4s2. If calcium loses 2 electrons, it acquires the configuration of argon. So calcium loses 2 electrons and forms an ion, and this ion, calcium ion, has a charge of 2 positive. Fluorine, on the other hand, is the 9th element. It has 7 electrons in its outermost shell, and it gains 1 electron to acquire the configuration of neon to complete its octet, and the ion that is formed is known as the fluoride. Now, again, due to calcium, which is positively charged, and fluoride, which is negatively charged, how would they stay together? Tell me. The molecule that is formed, or the bonding that is formed, the resultant whatever the resultant species that you get should also be electrically neutral. So for one fluoride which has one negative charge, and for calcium which has two positive charges, so what would happen? A calcium with two positive charge will have to combine with two fluoride ions. Why two fluoride ions? Why would it be two fluoride ions? Because there would be now two negative charges. So the compound that would be formed would be CaF2, right? The compound that would be formed would be CaF2, and now the glue that is holding this together to form a calcium fluoride is the electrovalent bond. And this time we have three atoms in the species. Actually, you do not call them molecules, but for the time being I'll call it the calcium fluoride molecule. So this was the Kossel-Lewis approach and what they said about the chemical bonding, about electrovalent bonding. Now Kossel and Lewis also said that it is possible for molecules to either lose or gain electrons, but the third possibility is to share electrons. Now imagining the atom to be a rigid cube limited their, how could they really show that kind of a covalent, that kind of a bonding by sharing of electrons? Now I told you that when a bond is formed by the transfer of electrons, if you really see what has happened here, sodium lost an electron and chlorine gained that electron. So if you really see, sodium has actually transferred its electron to chlorine to form sodium chloride. Such a bond which is formed by the transfer of electrons is known as electrovalent bond, while a bond that is formed by the sharing of electrons is known as a covalent bond. Now in 1919, Lewis along with another scientist, Langmuir, they gave the concept of a covalent bond. They shed that idea of a rigid cube, or the electrons occupying the corners of a cube, and it was Langmuir who modified the Lewis idea, and he said that there is no rigid cube around them. The electrons are present. You can imagine them as the Bohr's model, and he used the same Lewis structures and he advanced it further to explain the second type of bonding, which was formed by the sharing of electrons. Now, for example, if you take two atoms of chlorine and chlorine, what did he say? That chlorine has 7 electrons in its outermost shell, so he made the 7 electrons around it, and the chlorine here, and what did he do? The paired electrons he kept on the outside, and the unpaired electrons, he kept the unpaired electrons of different atoms, he tried to keep them between the two atoms. And then what did he say? That the orbitals of they didn't know orbitals, they said the valence shell of the outermost shell of the two atoms, it overlaps. And it overlaps in such a way that the two electrons which were not paired and were present on the two different atoms, they somehow fall between the two, and this pair of electrons is shared between the two atoms equally. They contribute, each atom contributes 1 electron, and when they do so, this area of overlap, these two electrons now belong to both the atoms. So chlorine, which had 7 electrons of its own, has got 1 electron from the neighboring chlorine atom, thereby forming a covalent bond. This type of a bond, which was formed by the sharing of electrons, this was known as a covalent bond. So we found that there were 2 types of bonding that was taking place. The electrovalent bond, which was formed by the transfer of electrons from one atom to the other, and the covalent bond, which was formed by the sharing of electrons. But the aim of all atoms was the same, to achieve that magical number of 8. In order to complete that octet, they would combine either combine to share or to lose or gain electrons to form molecules. Another example of this would be like chlorine. You could have a water molecule. Hydrogen has 1 electron in its outermost shell. Oxygen has 6 electrons. So we keep the lone pair, the single electrons between the two hydrogens. Hydrogen has 1 electron. Now what did we do? Every hydrogen has 1 electron. Oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. And now we draw this in such a way that oxygen shares a pair of electron with this hydrogen and this hydrogen. Hydrogen has 1 electron, and since hydrogen has only 1 shell, it cannot acquire the octet. It can only acquire the duplet. That is, it can only have 2 electrons. Why? Because the first shell has the maximum capacity of 2 electrons. It can never have 8 electrons. It is too small, too close to the nucleus to occupy 8 electrons. Therefore, hydrogen, it also shares 1 electron with oxygen. This hydrogen also shares 1 electron with hydrogen. So both the hydrogens, they get their duplet completed, while oxygen gets its octet completed by combining with the 2 hydrogens, thereby forming 2 single covalent bonds with the 2 hydrogens. Now these covalent bonds need not always be single. They sometimes can be multiple bonds. For example, in carbon dioxide, carbon has 4 electrons in its outermost shell and oxygen has 6 electrons. Now we find oxygen has 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. And carbon has 4. I'll make them like this. I'll explain to you why I did this. Carbon has 4 electrons of its own. In order to acquire the octet, it needs 4 more electrons. Oxygen has 6 electrons. In order to acquire its octet, it needs 2 more electrons. You know this by logic. So what do we need? What do we understand from this? That oxygen is going to form 2 bonds and carbon is going to form 4 bonds, because carbon needs 4 electrons, and if they are sharing electrons, we should place those many electrons between these atoms. So what do we see now? If we draw the circles, the oxygen combines with 2 atoms of carbon. This oxygen also combines with 2 atoms of carbon. So the octets of the oxygens are completed, and carbon combines with 2 electrons of this oxygen, 2 electrons of this oxygen, and it had 4 electrons of its own, 2 from this oxygen and 2 from that oxygen. It completes its octet. But what did we see here? Instead of having 1 covalent bond, here the carbon shows 2 covalent bonds with both the oxygens. So this is known as a double bond. We call it the double bond. Remember, the first bond here is a sigma bond and the second is a pi bond. The first is a sigma bond. The first bond between any 2 atoms is always a sigma bond. A sigma bond is formed by the head-on overlap. These, if you imagine these to be p orbitals, there is an overlap between these 2. And if there's an overlap, this is a head-on overlap. The electrons will be in this lobe in the middle, and they are being equally shared by the 2 atoms. So we say that kind of a bond is a sigma bond, the first. But we know p orbitals are along the 3 axes. So if this is the x-axis, the next bond, the second bond that has to be formed between p orbitals cannot be formed by head-on overlap, because one head-on overlap has already taken place. So the other 2 p orbitals are perpendicular to this. They are either present in this direction or in this direction. So the second bond that is formed by the sideways overlap. Is formed by the sideways overlap of the p orbitals. Such a bond which is formed by the sideways overlap is known as a pi bond. Right? So the second bond that is formed is a pi bond, while the first bond is a sigma bond. It's just a directional thing, that the first bond is stronger because it is formed by the head-on overlap, and the second bond is slightly weaker because it is formed by the sideways overlap. But the octet definitely is completed and the magic number is acquired and the compound becomes stable. Let us take another example here now. Let us take ethine, right? Or a nitrogen molecule. Nitrogen has 5 electrons in its outermost shell. How many does it need to complete its octet? It needs 3 electrons to complete its octet. So, nitrogen, if we draw the dots, we know 3, so let us make those 3 in between these. Right? And 3 plus 2, we know they should occupy single coordination sites. Now let us overlap them. Since there should be an overlap of 3 electrons, we'll occupy these 3 between the 2 nitrogens. So each nitrogen had 5 electrons of its own, and it shared 3 electrons from the neighboring nitrogen, thus resulting in the formation of a triple covalent bond. Right? So this resulted in the formation of a triple covalent bond. So a covalent, now what would the triple covalent bond be? The first one, of course, would be a sigma bond. The second would be by the overlapping of y-axis. Let us say if this was x-axis, the y-axis, and the third bond would be formed sideways overlapping of the z-axis. So only the first bond which is formed is a sigma bond. The other bonds, the other 2 bonds in covalent bonding in a double bond or a triple bond would be pi bonds. So this is how the molecules are formed by the overlapping of orbitals or the outermost shells in order to share the pairs of electrons to form covalent bonds and to acquire the octet. This was all for this video. In the next video, I'll move on and I'll explain to you how to make these structures for different molecules, the Lewis electron dot structures, and we'll do this in much more details. If you found the video helpful, please give it a like and subscribe to my channel, suggest it to all your friends, and please keep returning for more videos in chemistry. Thank you for watching.